Classifications of oil. 1. Control oil. Sources until turbine reaches rated RPM, AOP, after that MOP. Pressure is 7 to 8.5 kg/cm2. Purpose is to establish trip oil, auxiliary trip oil, startup oil, auxiliary startup oil, auxiliary secondary oil, primary oil, etc. Color code is yellow. 2. Trip oil. Source is main trip valve, MTV. Pressure is 4.5 to 6 kg/cm2. Purpose is to reset, open end trip main and reheat stop valve. Color code is red. 3. Auxiliary trip oil. Source is main trip valve, MTV. Pressure is 4.5 to 6 kg/cm2. Purpose is to trip hydraulic trip device. Color code is stripped red. 4. Startup oil. Source is starting and load limiting device, SLLD. Pressure is 5 to 6 kg/cm2. Purpose is to assist resetting and opening stop valves. Color code is brown. 5. Auxiliary startup oil. Source is starting and load limiting device, SLLD. Pressure is 5 to 6 kg/cm2. Purpose is to reset main trip valve and hydraulic trip device. Color code is stripped brown. 6. Auxiliary secondary oil. Source is speeder gear. Pressure is 2.3 to 4.8 kg/cm2. Purpose is to give input signal to hydraulic converter. Color code is stripped blue. 7. Secondary oil. Source is follow-up pistons and electro hydraulic converter. Pressure is 0 to 6 kg/cm2. Purpose is to govern HP and IP control valves. Color code is blue. 8. Primary oil. Source is turbine rotation. Pressure is 0 to 2.5 kg/cm2. Purpose is to give feedback signal to hydraulic governor. Color code is parrot green. 9. Test oil. Source is overspeed test devices. Control oil. Pressure is 2 kg/cm2. Purpose is to check free movement of fly bolt and pawl. Color code is violet. Last is drain oil. Color code is chocolate. As soon as AOP is started, control oil generates and passes through oil filters and directly reaches up to remote trip solenoid valve. If we reset turbine, RTSVs will be de-energized and gives passage to control oil and isolates drain port. Control oil leaving from RTSV called trip oil and reaches up to main trip valve. If turbine trip signal generates, RTSVs gets de-energize command and bridge of control oil to trip oil cuts. Control oil blocked at entry chamber and downstream circuit of trip oil connects with drain. Thus on draining of trip oil, MTV oil circuit also drains out and ESV closing takes place. The oil coming into main trip valve is control oil. And leaving MTV is called trip oil and auxiliary trip oil. MTV is spring-loaded valve, no electrical or other source available. It means through only auxiliary startup oil, MTV can be reset and trip oil generated. But, yes, to trip MTV or to kill trip oil, manual lever is provided. Control oil buildup at the entry point of MTV after resetting remote solenoid trip valves, RSTVs. But cannot flow into MTV. As SLLD moves from 100% to 0% position, auxiliary startup oil generates and comes to MTV bottom side. Continue raising pressure of auxiliary startup oil pushes pilot valve of MTV upwards against downward spring force located at the top of MTV portion. By this pilot valve upward movement, control oil port exposes and drain port isolates. Naked port allows control oil to come inside and divides itself into two oil, trip oil, and auxiliary trip oil. Once auxiliary startup oil is generated with sufficient pressure, it holds MTV in reset position against spring force as internal mechanism is constructed so. It means to reset MTV, auxiliary startup oil push is required. But once it gets reset and auxiliary trip oil generates, no need of auxiliary startup oil. That's why at the upward movement of SLLD, from 0% to towards 100%, auxiliary startup oil drains out but MTV doesn't trip. Tripping of MTV. To trip MTV once manual lever is pressed, drain port of MTV gets exposed and auxiliary trip oil strength becomes less. Manual lever pressing force with spring force moves pilot valve downwards and cut the control oil circuit port. Trip oil as well as auxiliary trip oil get drained through drain port and thus ESVs get close. As soon as AOP is started, control oil generates and passes through oil filters and directly reaches up to remote trip solenoid valve as well as starting and load limit device. If we reset turbine, RTSVs will be de-energized and gives passage to control oil and isolates drain port. Control oil from RTSV reaches up to main trip valve. Control oil is blocked at both ends, at MTV and SLLD. From DCS, lower SLLD command leads control oil entry to SLLD and divides itself into startup oil and auxiliary startup oil. Startup oil reaches to test valve and pushes piston downwards and make arrangement ready for entry of trip oil at upper portion and blocking of trip oil at lower portion. Parallel auxiliary startup oil pushes upwards piston of MTV and gives passage to control oil to enter inside MTV. Entered control oil finally divides into trip oil and auxiliary trip oil. Trip oil directly flows to ESV test valve. Main trip valves are now held in their upper position by the auxiliary trip oil pressure under their stepped differential pistons. Test valve allows trip oil to build up pressure space above piston Ka01 of main and reheat stop valves and forces it down against piston discs Ka02. Operation of the starting and load limit devices continued until piston discs Ka02 reach their lower end position. Ka01 and Ka02 clutching covers drain port provided into ESV for very quick closing during abnormality. When handwheel Ka01 is turned back or motor of SLLD is operated in the open direction, the control oil is allowed to drain first from the auxiliary startup oil circuit and then from the startup oil circuit. After resetting MTV, auxiliary startup oil has no role in MTV until next trip. The pistons of test valves are forced upwards by the restoring springs whereby the trip oil flows to the space below piston disc Ka02 and slowly drains from the space above piston Ka01. The pressure difference thus occurring lifts both piston and piston disc together into their upper end positions, thus causing main and reheat stop valves to open. Vacuum trip hydraulic device. Assumptions. 1 turbine on barring gear. 2 vacuum pulling will be started shortly. 3 governing oil circuit already charged. In slide, alphabet A presenting spring force exists against diaphragm, B against control oil chamber piston and C against tripping chamber piston. In this condition control oil enters into device but remains trapped inside device chamber. As we started vacuum pulling in condenser, negative pressure pulls diaphragm upwards against spring force, A, and thus piston also moves upward with it. Upward movement allows control oil to flow in tripping chamber, raise up piston against spring force, C, and blocking auxiliary trip oil pressure at entry. But still vacuum low hydraulic trip not in service. As turbine rolling starts, primary oil buildup and at certain pressure, before rated RPM, clutching of adjustable lever takes place and which opposes vacuum force and thus finally vacuum trip comes in service. So as per the device construction, if vacuum starts dropping, diaphragm and piston assembly starts downward movement. If vacuum is more than 0.3 kg/cm2, summation of vacuum force and spring force B is greater than primary oil force and spring force A. Exactly at low vacuum tripping value 0.3 kg/cm2, summation of vacuum force and spring force B becomes equal to summation of primary oil force and spring force A. How low vacuum device tripping takes place. If vacuum drops below 0.3 kg/cm2 value, force of primary oil and spring A becomes greater than the force value of vacuum and spring B, and thus diaphragm and piston assembly blocks control oil entry into tripping chamber, and drain port exposes. Exposed drain port drained out the control oil, which kept tripping piston in hold position. As tripping piston becomes unrestricted from downward movement, spring force C quickly push it down and drains out auxiliary trip oil. Vacuum trip hydraulic device. Assumptions. 1 turbine on barring gear. 2 vacuum pulling will be started shortly. 3 governing oil circuit already charged. In slide, alphabet A presenting spring force exists against diaphragm, B against control oil chamber piston and C against tripping chamber piston. In this condition control oil enters into device but remains trapped inside device chamber. As we started vacuum pulling in condenser, negative pressure pulls diaphragm upwards against spring force, A, and thus piston also moves upward with it. Upward movement allows control oil to flow in tripping chamber, raise up piston against spring force, C, and blocking auxiliary trip oil pressure at entry. but still vacuum low hydraulic trip not in service. As turbine rolling starts, primary oil buildup and at certain pressure, before rated RPM, clutching of adjustable lever takes place and which opposes vacuum force and thus finally vacuum trip comes in service. So as per the device construction, if vacuum starts dropping, diaphragm and piston assembly starts downward movement. If vacuum is more than 0.3 kg/cm2, summation of vacuum force and spring force B is greater than primary oil force and spring force A. Exactly at low vacuum tripping value 0.3 kg/cm2. Summation of vacuum force and spring force B becomes equal to summation of primary oil force and spring force A. How low vacuum device tripping takes place. If vacuum drops below 0.3 kg/cm2 value, force of primary oil and spring A becomes greater than the force value of vacuum and spring B, and thus diaphragm and piston assembly blocks control oil entry into tripping chamber, and drain port exposes. Exposed drain port drained out the control oil, which kept tripping piston in hold position. As tripping piston becomes unrestricted from downward movement, spring force C quickly push it down and drains out auxiliary trip oil.
Healthiness of governing system components are essential. To ensure fault-free operation in turbine load condition time, ATT is programmed. That is why many SOV and hydraulic valves are introduced. In the ATT, ESV operation on load, are TSVs and MTVs testing covered. Basic concept to carry out governing component testing operation without tripping the turbine. Tripping will take place if trip oil circuit will be drained. ATT will supply trip oil from alternate way to CVS and other ESVs to keep turbine on load, and only MTVs and RTSVs testing will be carried out. As you know, MTV outlet trip oil goes into ESV operation, as well as in control valve operation. To keep functioning other ESVs and control valves during testing, MTV outlet side available trip oil should be provided by other source, and then RTSVs, MTVs and ESV testing possible, so that turbine will not be tripped. As the circuit shown in slide, trip oil generated from MTV is supplied to ESV as holding pressure, and to follow-up pistons as regulating pressure for opening and closing of control valves. Some arrangement needs to be provided on outlet of MTV which can continue supply trip oil during testing. That is why MAX51, AA001/002 is introduced, to supply control oil, as a trip oil, into MTV outlet trip oil line, with one hydraulic changeover valve MAX51, AA211. One SOV MAX61, AA201 is also provided to change the port of changeover valve. Now test the SOV MAX51 AA201 and 202 operation, that it sufficiently build up oil pressure in the alternate line, which we will use as a trip oil to other ESVs and control valves operation, during testing period. So energize first MAX51 AA202, and check the pressure switch MAX51 CP205, installed in between two SOVs. If this pressure switch actuates means, oil pressure developed sufficiently. After that energize max AA201, and check the pressure switch installed after this SOV MAX51 CP207. Both pressure switches actuation conforms the path up to the changeover valve MAX51 AA211. Now by changing the port of the changeover valve, testing trip oil will take over the path from main trip oil circuit, and back loop, MTV, RTSVs are no more in operation. To do so, energize the SOV MAX61 AA201, and pass the control oil to changeover valve upper side port, which swaps the port and allows the testing trip oil to flow in ESV and control valve circuit.
RTSV and MTV testing. After ensuring the test trip oil healthiness, ATT will give energize command to RTSV2. Energizing of SOV RTSV means, downstream of oil towards MTV, drains out and cut off the intake oil. Trip oil draining would be confirmed from the pressure switches MAX51 CP209/210, installed in between the MTV and changeover valve. Also from the MAX51 CP203/204 installed in between MTV and RSTV. On actuation of pressure switches, RTSV's fault-free operation is confirmed and ATT will start latching operation of RTSVs.
RTSV latching. After completion of testing RTSV, again trip oil from RTSVs to be established by de-energizing the RTSVs. By doing so, trip oil flows up to the MTV inlet port. Low pressure switch MAX51 CP203/204 deactivation confirms the oil flow through RTSVs.
MTV latching. RTSV oil reaches up to MTV, but cannot flow inside the MTV port, and thus trip oil as well as auxiliary trip oil still not generate. To generate those oils, MTV should be reset by auxiliary startup oil. To generate auxiliary startup oil, SLLD downward movement is required, which is not possible as turbine is on load condition. So alternate SOVs are provided, which will supply control oil, in the port of auxiliary startup oil, to reset MTVs. By giving command to SOVs MAX48 AA201 and 202, control oil will direct enter into auxiliary startup oil line, and reset MTV by bottom push. Bottom push will open the entry port of RTSV oil, and thus trip oil and auxiliary trip oil will generate. Healthiness of trip oil will be confirmed by pressure switch max 51 CP209/210. And healthiness of auxiliary trip oil will be confirmed by pressure switch max 52 CP211/212. Isolating the test trip oil supply. After successful completion of MTV latching, trip oil should be supplied to ESVs and control valves, as per actual scheme, from RSTV MTV loop. Supplied test trip oil needs to be cut off. For that, control oil supplied to changeover valve port swapping should be cut off by de-energizing SOV MAX61AA201. Afterwards, de-energize the SOV's MAX 51AA201/202. Also, check the pressure switched status installed in the lines. It states that original scheme of trip oil circuit is taken in service. Cautions: the main stop valves MAA10, AA001 and MAA20, AA001 may only be tested at a load that is less than 60% of the maximum output. First, the main control valve concerned, MAA10 or 20AA002, is to be closed slowly by turning handwheel KA09 on the actuator. EHTC load control mode will open the other main control valves accordingly, to maintain load. Once the control valve has been shut, the stop valve can be closed. ESV is to be reopened immediately. The main control valves may be closed for testing purposes for not longer than 4 to 5 minutes, so that the unbalanced steam flow is only present for a short period, to avoid significant effects on the HP turbine casing.
ESV-ATT procedure. Let's assume that among 4 ESVs, ESV1 is selected for testing. First step is to close the control valve of the same ESV slowly by turning handwheel KA09 on the actuator in field. Slow closing of control valve is very important, as same steam load is distributed to remaining control valves and constant pressure also required. Once local reading ensures the tight closing of control valve, next step can be processed.
If the control valve has closed properly, solenoid valve MAX61AA211 is energized. This blocks off the passage of trip oil through solenoid valve MAX61AA211 and connects the space below piston disc KA02 with drain. The pressure in this space drops rapidly and is monitored by pressure switch MAX51CP223. When the pressure at this pressure switch has dropped slightly below the breakaway pressure of piston disc KA02, monitoring of the stop valve closure time starts. Limit switch CG001E enunciates entry of the valve into its closed position, thus making it possible to monitor the valve closing action for completion within the maximum running time.
ESV reopen procedure. Next, solenoid valve MAX47AA211 is energized, test position, and trip oil is released to the control surface of the piston in test valve MAX47011. The piston moves into its lower end position, against the spring force, thus permitting trip oil to flow to the space above piston Ka01 of the stop valve. This piston is forced downward by the pressure of the oil, thereby tensioning the spring between piston Ka01 and piston disc Ka02, and finally pressing against piston disc Ka02. Up to this point, the oil pressure above piston Ka01 is relatively low, being equal to the spring force acting against it. The spontaneous pressure rise, when piston Ka01 has made contact with piston disc Ka02, and thus on completion of the spring tensioning action, is detected by pressure switch MAX51CP222. If all conditions are fulfilled, within this relatively long monitoring period, solenoid valve MAX61AA211 is de-energized, operating position, so that trip oil is once again able to flow to test valve MAX47AA011, and the drain is blocked off again. The buildup of trip oil pressure is monitored by pressure switch MAX51CP221. When the pressure is sufficiently high, the stop valve is opened by de-energizing solenoid valve MAX47AA211, operating position. Test valve MAX47AA011 switches over, admitting trip oil to the underside of piston disc Ka02, and after a certain amount of further travel, slowly connects the space above piston Ka01 with the drain. The resultant pressure difference causes the tensioned piston relay to open the stop valve. As soon as the open position is reached, the full trip oil pressure builds up. This is monitored by pressure switch MAX51CP223 and by limit switch CG001D. Testing of stop valve is now completed.
Overspeed tester operation on load. It is called oil injection test 2. Overspeed trip device MAY10AA001 and MAY10AA002 can be tested using mechanical overspeed trip test device MAX62AA001 or MAX62AA002 respectively, with the turbine running either on load or off load. To operate the test device, valve Ka03 is first pushed in, and held in this position. This isolates the auxiliary trip oil circuit from the overspeed trips, and inhibits initiation of turbine trip by the overspeed trips. After this, by way of energizing overspeed trip test solenoid valve MAX62AA201 or MAX62AA202, center valve KA01 is moved downward. This action blocks the drain, and test oil is injected via a jet into the oil spaces of overspeed trip MAY10AA001, or MAY10AA002. The oil mass injected fills the oil pan for the striker, and the resulting increase in centrifugal force causes the trip striker to overcome the spring force at rated speed. The trip striker flies out radially and strikes the pawl of the overspeed trip release device, as a result of which the associated valve moves rapidly inward. Then, the pressure in the auxiliary trip oil circuit, up to the overspeed trip test device, collapses. Confirm the pressure gauge, MAX52CP501 or MAX52CP502, to 0 kg/cm2.
As soon as auxiliary trip oil pressure drops to 0, at pressure gauge MAX52CP501, or MAX52CP502 to 0 kg/cm2, center valve KA01 is released and returned to its original position by spring force. Confirm the pressure in the test line should then return to 0, as can be read off at pressure gauge MAX62CP501 or MAX62CP502. The overspeed trip devices then return to their original position. When overspeed trip devices return to original position, valve KA02 must be pushed downward, and held in this position, to admit control oil into the auxiliary startup oil circuit, to the differential piston of the overspeed trip release device. Confirm the valve moves outward and latches in again. Confirm the build-up of pressure, in the auxiliary startup oil circuit, between the overspeed trip test device and the overspeed trip release device, can be followed at pressure gauge MAX48CP501 or MAX48CP502. Valve KA02 can then be released so that auxiliary startup oil pressure falls to 0 and auxiliary trip oil pressure must then remain at its full value. After confirmation of auxiliary trip oil pressure at its full value, through pressure gauge MAX52CP501 or MAX52CP502, valve KA03 can be released and the test is completed.